In this video, we present a method to plan safely with learned dynamics. We bound the error between the learned and true dynamics with two quantities, the Lipschitz constant of the error and the maximum training error over our dataset. We apply filtering to determine where our model is good. We then build a trusted domain D that is a union of balls about points in our training set. In this domain D, the difference between the learned and true dynamics can be uniformly bounded. With the uniform bound, we use the LMTD RRT to plan trajectories with two key properties. The first is that each point in the trajectory is in a strictly smaller set than D. The second is that there exists a one-step feedback law at each point along the trajectory. To illustrate, consider the following, where we plan to go from x0 to x1 under the learned dynamics. However, under the true dynamics, we end up at some x tilde 1, which is within a distance epsilon of x1. We guarantee the existence of a feedback law that brings us back to x2 under the learned dynamics. Under the true dynamics, we end up at some x tilde 2. Again, we compute the guaranteed feedback that brings us back to x3 under the learned dynamics. The process repeats until we reach the goal. We can use the same guaranteed feedback law to stabilize about the goal indefinitely.
We plan for a 6-dimensional quadrotor in the presence of obstacles. Plans computed using LMTD-RRT can be tightly tracked in execution. This is due to our method constraining the planner to only explore regions where the learned dynamics model can be trusted. In contrast, using a naive kinodynamic RRT can return plans which cannot be tracked, causing divergence and crashes in execution. We plan for a 7-DOF arm, going from below to above a table. Again, we see here that the plans computed using LMTD-RRT can be tightly tracked in execution. We animate the nominal plan by playing the state space trajectory that is generated under the learned dynamics. The open loop trajectory is the set of states that is visited when applying the sequence of control actions from the planner on the true dynamics. The closed loop trajectory is the set of states that is visited when applying the one-step feedback law on the true dynamics. However, a plan returned by a naive kinodynamic RRT exits the trusted domain, exploiting errors in the learned model, resulting in open and closed loop executions which collide with obstacles and fail to reach the goal. This suggests that it can be crucial to plan trajectories which explicitly remain within the trusted domain of the model in order to ensure safety and goal reachability.